Let's look at a mechanism for dehydration. This was a question, post-lab question from experiment 10, cyclohexanol to cyclohexene. We have a molecule here is in cyclohexanol. It's a 2,2-dimethyl cyclohexanol with concentrated sulfuric acid. It makes the alkene, which is a 3,3-dimethyl cyclohexone. Let's take a look at the mechanism. Now, the mechanism, instead of using H2SO4 directly, we're going to use H3O+. This is a nice representation for a lot of acids, a generic acid. Besides H2SO4, when it reacts with water, it makes H3O plus and HSO4 minus. So it makes sense to use this. It's easy to use. What we have here is this is the acid without the arrows. We're going to put the curved arrows in to show the mechanism. So the first step is what's called the protonation step. Protonation, because we have a strong acid, that lone pair is going to pick up the proton. The next step in this protonation is we got to get this bond between the oxygen and hydrogen will shrink to become a lone pair on the oxygen. That'll make water. Okay, so let's make that, let's draw the structure of these, of what the arrows tell us. So the arrows, as you could see right here, tells us that we have a protonated alcohol. What we have done is added the H and also the plus charge. You have to add the formal charge to the oxygen. The next step is a loss of the leaving group. Water is a really good leaving group because it's a neutral molecule. If you have a chloride, bromide, or iodide, those are really good leaving groups because then they are stabilized negative charges by the large size of the ion. Okay, so let's draw what happens to this water molecule. We form a carbocation. So this is a carbocation that is made. As you can see that when the water leaves, we put a positive charge on this carbon, it becomes a carbocation. Now it'd be a good idea at this point to label the beta carbons, the carbons that are next to this carbocation's carbon. The carbocation carbon, that carbon, we could call it the alpha carbon, and next door to it are the beta carbons. We'll just put B's to represent the beta carbons. Now, what you need to do is you need to take a look at the structure, which is the product, and we're going to form a double bond at that position. Okay, so you have to identify that the beta carbons have hydrogens that you could abstract. Only one allows you to extract the hydrogen. It's implied that the two hydrogens are here. We only need one. So that's why I'm going to put one in. And this is going to be abstracted by water because we have lost water. So water comes in and abstracts it. So let's put a water molecule here. And we're going to pick up that proton to regenerate our. It's going to bring in the lone pairs. Okay, I like to use lone pairs for oxygen. So you got those lone pairs that stretch out, pick up the proton. Okay, so make sure you point at the hydrogen because that's what you're picking up. And then this bond becomes a double bond. This bond between the hydrogen and carbon, we make an arrow, have an arrow point at the position in the middle between the two carbons to get the alkene. And this is the mechanism for this product. This is actually a minor product in the reaction, but it it's good to know how to do the mechanism. Now let's take a look at other possible products that could be obtained from this. In order to do this, we'll take a look at the carbocation that was generated. Okay, by looking at this carbocation that was generated, we're going to do is we're going to see if there's any chance that this secondary carbocation, because it's flanked by two beta carbons, could become a better carbocation. If we move the hydrogen over, then that will be the new carbocation center into secondary. So there's no way this wants to go from a secondary to secondary. But there's a chance that this secondary carbocation could be rearranged to a tertiary carbocation. In order to do this, what we have is these methyl groups. One of the methyl groups will transfer over, become a CH3 minus, and now it will attach to this carbon that was positively charged. So let's take a look at what carbocation you could generate from this. Okay, so the methyl shift has allowed us to generate a new carbocation, and you can see that this carbocation is now flanked by three carbons, so this is now a tertiary carbocation. Again, at this point, it'd be good idea to label these carbocations, or the beta carbons around the carbocation. So we have three beta carbons, and those beta carbons indicate this is a tertiary carbocation, which is much more stable than a secondary carbocation. Now, in order to identify any other possible products, make sure that your beta positions, you could identify whether there's hydrogens on there. So let's take a look. There are three beta carbons, and if you take away a proton from this top one, we could call that beta 1 if you want, you form a double bond right here. Okay, let's make that product. Okay, so I made the product right here. It's a double bond from the beta carbon's hydrogen. So this carbon hydrogen, if you want, we could even throw that hydrogen in here. Oops. And this is the hydrogen that water is going to abstract to form a double bond to make this alkene. Okay, let's take a look at other possible alkenes that could be made. How about the one down here? This is the other beta position. There's a proton here that we could abstract, and then we're going to put the proton in here. And that allows us to make a new double bond along here. Okay, as you can see, we got another possible product. And oops, don't forget to get rid of the carbocation, the positive charge, because there's no longer a positive charge here. And this is the other product, as we could form a double bond down here. Now, the next product is one more beta carbon, this one. And if we were to make a double bond there, there's hydrogens on that terminal carbon. And we just to get rid of some other positions right here, there's one more beta carbon. We could make a double bond here. And these are the four possible products for this reaction. Oh, it's a beta carbon down here. Okay, so these are the four possible products. Now remember, we did only the first mechanism, the mechanism of the first product. The second product is easy to do a mechanism. First, we had done a rearrangement reaction, so to get this carbocation. Once we generate that carbocation, we could go and make any of these three other possible products. Okay, so again, we can put a hydrogen here. Water is just going to pick up this proton. Let's just change the positions a little bit. Makes it better to have the hydrogen on that side that it's going to make a double bond. Okay, and so water is going to come in. It's really nice to put the lone, it's good to put the lone pairs in here. Okay, here's a lone pair. Here's another lone pair. So water is going to have the lone pair pick up a hydrogen. This is going to form a bond. And now this guy goes in the bond between the hydrogen and the carbon, that's beta carbon, makes a double bond to make this alkene. So remember E1 reactions and SN1 reactions, we have carbocation and carbocation rearrangements possible. For E1, water comes in, picks up the proton, and makes a double bond. We could do the same thing for this one. Hydrogen's down here. Water comes in to pick up this one, forms a double bond to make this. And then the third one was the CH3 here. One of the hydrogens will be abstracted by water, just like we have done here.